Okay, better. So, today we have a first lecture here in Växjö for my part on this network interaction course. Did you check the lecture last week from the stream? Any questions about it? Anything? Was it working? Fine. Okay. Good. Could someone please be on the Slack channel while we have the lecture now and see if someone asks a question remotely and then pass it on to me, because I couldn't get onto the Slack here at the same time. So just say if someone asks questions. Right, so let's move on to mixing here. So today, as you see, we'll talk about network performance. So last week we talked about routing protocols, and hopefully you already seen that much of the last assignment is already out, except the actual assignment, but a lot of information about it. And that will be about what we talked about last week. But make sure that you get the environment GSM-free working. I just checked it now last week and saw that they have a new version and a new way to distribute it. So you may have to play around with it for a while. But hopefully it will work. But today we'll continue then with network performance. And there are quite a few things we'll talk about. So we'll talk about different ways to actually measure networks, what is interesting to look at, and different problems we can see when we measure it and the result of that measurements. And then at the end we'll talk about, okay, what can we now do then? Why do we measure? What can we use this information for? And can we control the network so we can control these measurements that we get instead of just passively measuring what we get? And that is then the quality of service. And there are different ways to implement that. So we'll look at performance, how to measure the performance, and how that will affect the transmission of packets then. Depending on the type of network we talk about now, they have different possibilities to actually use this. And of course, we will mainly think about the internet as the case now. So think about the TCP/IP network, probably with a local LAN network where they have some Ethernet and then remote links using different type of technology. So we have this merged network with different type of technology used. But it's a TCP/IP network that we will have as the case study here. But some of the ideas that we'll talk about today come from earlier type of network technologies, and that has influenced how we talk about quality of service actually today. So when we measure a network, what do we measure? What do we conceive? Well, the term speed is often used. What is the speed of your network connection, or what is the speed that you have when you transfer something? So that is what we often say, and we can talk about low speed or high speed network. What that is of course depend over time. So that's not a really good measurement or good way to describe it. When I started with networking, my first remote connection was with a 300 baud modem, so 300 bits per second. And that was the high-speed network at that time. So things are changing, luckily. So we really need to measure instead what it is. What is the speed, and should we actually use speed, or could we say something other? And what other things can we measure in the network, except for how fast things goes, how quickly bits are transferred? Well, we'll mainly talk about these three measurements that we can talk about in network. The first one is latency or delay. Latency is the time required to transfer something from the starting node to the end node. Many times we talk about the round trip delay, so sending it somewhere and then get a reply back. Why use that instead of just in one direction is because that is much easier to calculate. So then we often do that. But it can be just one path as well, one way. So that's the delay or latency. As you see, delay is quite tricky actually, because there are lots of different components in the delay that we have to think about. Then we have what we may call speed then, or throughput. And when you talk about capacity, we more talk about the theoretical maximum of what we can get. And throughput is the actual number of bits per second that we can transfer. So these are the two main measures that we can, or types that we can measure. And then at the end we also have the jitter, variation in delay, that sometimes is important, sometimes not. But let's start to talk a little bit more in details on the latency then. So how long time it takes for data to travel then through the network. So we are starting in one node, and now we put a packet or a bit, really depending on the type of network technology we're using, onto the network interface, and then it starts to traverse the network. And on the way, of course, it will depend on, again, the network. It will see different things. It might see a cable, that can be a coaxial cable, it could be a fiber cable, it might see a switch, it might see a router, it might pass through a satellite, whatever. It will go through a number of different things until it actually, at the end, reaches the destination. Normally we measure this in a fraction of a second, or typically we talk about milliseconds when we talk about network, how many milliseconds it takes, because that is a fair size that we can easily talk about the number of milliseconds. When we talk about users of a network, they of course are interested in the data that they see. You go to a web page and you start to downloading the information on it. What you are interested in is not really the network delay. What you're interested in is the total delay, including also what goes on the other side. When you click to get a web page, you send a command, and then the web server has to process that command. Maybe do a lookup in the database, combine different files, and then send all of the things to you. That can take time, and that is part of the delay that the user sees. So we have to make sure that we think about what is actual network delay and what is the total delay. We could be interested in different measurements, and then over time it can be the mean delay, it can be what the variation, maximum, minimum, and so on. So, and depending on the situation, we might be interested in different parts of that. But if we try to look then into the details, what is really adding up to this delay? Well, we have first one part that is propagation. The time required for the signal to transfer across a medium. What is the problem here? Why is there a delay at all? What is the maximum speed a signal can travel? speed of light, yeah. So regardless of what type of medium we're using, we can never go faster than the speed of light if we talk about propagation delay. And depending on what type of medium we're using, it will be lower than that. It's not the same propagation delay in all media, and depend on how we actually modulate the signal. If we use sound, for instance, as our way to send information, sound travels at a very slow speed then, compared to electromagnetic radiation. But for most purposes, it is close to the speed of light, so let's assume that. But that is not something we can just, okay, it's almost speed of light, then it doesn't matter, because if we go around the globe, the speed of light is actually time that matters. Then we have access delay. The time needed to obtain access to the transmission media. We have something we want to send, we have decided, okay, now we have a packet, let's put it onto the media. But we might not be able to do that immediately. The obvious example is, of course, if we use an Ethernet, where we have carrier sense, multiple access with collision detection. We have to wait for media to be available. So a shared media, there we have to wait. But it can also be that we have a single media, but we have several packets that need to go, and we couldn't send our packet until it's available for us. But think about an Ethernet typically here. Then we have switching delay, time required to forward a packet through different types of equipment. It goes into a router, then it has to make a lookup, it has to go through one input buffer and then send to an output buffer. And inside a device, it is much slower than the propagation delay that we have on the cable itself. So each device that we add, each node will add a significant amount of delay. Then we have queuing delay. We talked about routers last week. A router accepts an incoming packet, then looks at it, decides, okay, where should we forward it? It decides on an output interface, and then it puts it into a buffer, waiting, because we can have 10 packets arriving at the same time on different input interfaces that all should go to the same output interface. Of course, now they have to wait before we can actually pass them on. So these queuing delays can add up. And this is typically the one that contributes most to the delay. And then we have, from the user's point of view, the server delay as well. We send something, it's passed on through the network, it is computed on the server, and then we send this information back. The server delay is not really a network delay, but it adds up to what the users see as a delay, this round-trip delay. Now, if we look at these that are network-related, propagation, access, switching, and queuing, we can see that propagation delay is more or less fixed. I mean, we have a path from sender to destination. In most of the cases, we use the same path all over again, which means that the propagation delay is almost fixed. It doesn't change over time. The switching delay is also almost fixed. We pass through the same equipment, so it will take the same amount of time. Access delay can, of course, vary a little bit. If we are connected to a local network with a heavy load on it, it will take longer time before we can send something. But the one that is most variable is the queuing delay, because here we can wait for a very long time compared to all the other delays. So the total delay is variable, and the one that contributes most to the variation is the queuing part. And then, of course, the server, but that, as I said, is not really part of a network delay. So delay adds up, and the propagation delay, even if it's short, it is very much different depending on what path we take. Say we have, as an example here at the end here, we have a connection between two nodes, one that is ground-based, a fiber cable, and one that goes up to a satellite and then back down. That will be quite a lot in extra delay if we take the satellite link, because it's so far out. Now it depends on what type of satellite, of course. If we talk about these geostationary satellites, which are on the same place over Earth all the time, that means they are 36,000 kilometers out. In that orbit, all the satellites are standing still over the same place. So that's an interesting type of satellite to use for broadcasting, for instance, but also for data communication, because it's easy to point an antenna towards them. But it's very far out, so it adds a lot of delay. We have these LEO satellites, which are low orbit instead, which are much closer to the Earth, but that means they are moving all the time. That is used, for instance, for GPS. They are much closer to Earth, but there are also these low Earth orbit satellites used for data communication. So the good news is that they're much closer, they add lower delay, but you have to have active antennas that can follow them in order for it to work. So it's more tricky. But here we add, as you see, low orbit, maybe 20 milliseconds. A geostationary can add 100 milliseconds or a couple of hundreds milliseconds. So that's a long time. Well, access, I think we covered most of that already. The switching delay as well. And the queuing. We'll come back to talk about queues a little bit when we talk about quality of service. And then we have a server at this also. So we covered most of the delay now. So let's move over to throughput instead then, or capacity. So when talk about the capacity, as I said, it's the maximum possible throughput we have. If we use a fiber optic cable, we might have a 100 megabits or 1 gigabit per second. That's the capacity of that cable. That's the most that we can push in. The throughput that we get is what we actually get. And the throughput will always be lower than the capacity. There are, as you see, different possibilities when we are looking at throughput here. We talk about capacity of a single channel. Well, a channel is more of a soft definition, a logical channel. On a network we might have, on a physical cable we might have 100 logical channels that we can use. And then we can get allocation of one or several channels to use. They are working independently of each other. So the question is it a channel we're talking about, or is it actually the hardware cable? Which would be then the next row of the aggregate of all the channels on that cable. As a side note, we can say that when we split up a medium in this way, in logical channels, that is one way where we lose capacity, because it takes time to manage these different channels. So part of a capacity will be lost by just managing the different channels. But we can also do the other way around. We can actually merge several physical cables. We can do link them together. So we split our data stream onto several physical cables. And then the capacity we see is the aggregate of those together. so it can be more than one cable as well. Or it can be, as a last row here, the effective data rate that we see, or that an application sees when it communicates with another application. And then it also takes part, or has to include what is going on the other side, the delay or the computation that is done on that other side. And then we talk instead about good put, that is the effective data rate that we can achieve, taking also into consideration that someone has to handle the data that we are sending. So hardware capacity, the potential, the maximum, and so that's always an upper bound, because there are things that is limiting it. The effective data rate, we call what we actually get, and as I said, good put is the term that we can use here. Why can't we achieve the maximum, the hardware capacity? Well, there are a number of reasons of why we can't do that. So here we see some of the reasons. We have typically a packet. We are sending different type of packets. We format the data into hardware frames that are then put in logical packets, datagrams on. On all these levels that we are doing this encapsulation, we have headers, trailers, different type of control information. That is just there to control the data flow, but it doesn't give us actual data. So the more headers we have, the more capacity we're losing. Then we might have a window size, like for TCP. We have a window size. When we send something, the other side couldn't handle more than a number of bytes. And if we start sending more, the other side will say stop. And then we have to wait for the other side, which means, again, we lose possible capacity here. Then we use other protocols. When we send something, we can't start sending it immediately. We might have to use DNS to resolve a name. And then we might use ARP to get the Ethernet address. And we might use other supporting protocols. So we have to wait for that before we can actually do something. Again, we lose capacity. We might have congestion in the network. We want to send at the same time as a lot of others want to send. That means that queues are building up, and now we have to wait in different parts of a path. And of course, that will reduce the possible capacity. And then retransmissions. Whenever we have to retransmit something because it's lost, dropped, or deleted in some way, of course we will lose in capacity because we have to resend instead of sending new things. So there are a lot of things that add up to a lower actual capacity than the hardware capacity. As a good put is what we see as a user, but it doesn't really reflect what goes on in the network. So we have to make sure that we are looking, if it's the network we have in focus, we should actually see what's going on in the network, not what is going on the server or on the host on the other side. But it can be difficult to see what is really the network's fault and what is the other node's fault. So throughput, what is really throughput? Well, we use different terms for it. We already talked about speed. Is speed what we mean? We also have a term bandwidth that is also talking about how much information we can send. When we talk about bandwidth, that is more of a physical way to describe the capacity or the throughput. because bandwidth is connected to the frequency we're using to transmit a signal. I guess Morgan talked about Shannon's and Nyquist theorems, where we put a relation between the frequency of a signal we're using and how much data we can send on that signal. So we have a relation between the actual physical frequency we're using and the throughput. So the higher the frequency using, the more bandwidth we have available and the more data we can send. But bandwidth is not good to use if we talk about really network on a logical level. So that is more of a physical thing. So let's talk about throughput instead, use that as a term when I talk about the capacity or speed of a network. But it's not a speed as a normal speed, so that's why we shouldn't really use that term. So think about this one. Imagine a network is a road between two locations, and packets traveling are similar to cars. I mean, each car is a packet. It's independent, we send it out on the road, and it reaches the other end. Throughput then determines how many cars we can enter the road each second, how many data packets we can put onto that network. That gives us a throughput. The more cars we can put, or the more packets we can put, the better throughput we'll get. So it doesn't have to, it's not really related to the speed of a car. It's not how fast it's going on the network, it's how many we can put on the network during a certain time period. And the propagation delay is then how long time it takes to reach the other side. And of course that is more connected to the speed of the car, how long time it takes. So speed is related to both delay and throughput. That's why we should use throughput and delay instead. If you're starting having a problem with a network, you say that the throughput is going down for some reason. You use the network and you see worse and worse. You get less and less data, or the delay is increasing. What do you do then? Well, what can we do in a network? We can change technology, we can upgrade, we can add more links. What will that do? Well, if we buy higher speed cables or add more cables, what do we do? Well, typically what we do is we get more throughput. We can now send more data per second. But if a destination is still on the same place as before, it doesn't really change the delay. We still have to go the same way. We still have to go through the same devices. So more or less the delay will be the same. So it's easy to handle problems with throughput. We can upgrade the network. But it's much harder to do anything with delay. Of course, in extreme cases, we can do something about it. Say we're using sound, for instance, to actually transmit data. If we exchange that with a fiber cable, we will reduce the delay. But if we take a normal Ethernet cable and exchange it with a fiber cable, we wouldn't see much difference in delay. It will still be the speed of light, which is the limiting factor. So throughput is relatively easy to do something about. Delay is much harder. And then we have a third component here, the jitter. So jitter is the variance in delay. I mean, we now know that delay have more or less constant parts, but also variable parts. And these variable parts will make the appearance of the delay over time to have a variance. And of course the variance can be very different. The variance can be almost zero, so it's almost constant delay, because we don't have any changes in buffers. We don't never build up any buffers, so then we also almost have constant delay. But in other cases, we do build up buffers, and then we empty the buffers and build up new buffers and empty them, so the variance will be quite high. Sometimes we have low delay, sometimes we have a long delay, and that varies over time then. And that is jitter. And if we don't have any variance, we don't have jitter. So jitter is just the variance. And the more variance we have, the more jitter we have, and the more of a problem it typically is. So we can talk about the mean delay, but we also need to know about the variance really to know about this. And typically we try to at least put it between some boundaries. We have a mean value and then some upper and lower boundary around it. But in the worst case, of course, suddenly we lose connection. And then the delay goes up to infinity. We can't send anything at all. So there's no real upper bound for it. Why is jitter interesting? Well, it really depends on the type of traffic we're using the network for, if it is a problem or not. But say, for instance, we're using voice call over the network. And you start talking, and on the other side you're listening. And now if you have a variance here, so some packets get through with a delay of 1 millisecond, and the next packet takes half a second to get through, and the next packet again takes 1 millisecond, and so on. And if you now start to play up that sound as it arrives, you wouldn't understand what the other person says, because the sound will be so distorted that you couldn't really understand it. So if you need to have a steady stream of data like you would like for a voice call, delay is a problem. So you would like to have no jitter, but of course most real networks have jitter. So what can we do about it? Well, there are two main ideas how to handle jitter in networks. The first one is to build what we call an isochronous network. And an isochronous network is built in that way that there is no jitter. So the physical network have the property of giving you no jitter, or very, very small jitter at least. And the other option is to use a protocol that compensates for that jitter instead of trying to remove it from a network. So if we look back in history then and see what were the first networks that we had available. Well, the first networks we had were telephone networks. That was long before we had data networks, we had telephone networks. And how does a telephone work? Well, if we take the old telephone systems, it was really a physical line from one telephone to another. It went through a number of switchboards where people were sitting and actually connecting physical cables. So you had a physical link between the two people speaking. And when you started then to talk, the sound was sent over the wire. And of course, since you had a physical wire all the way, you had an isochronous network. You didn't have any variation in the delay there. It was just wire all the way. So that's a nice property of that type of network. Of course, there are lots of other problems with it, but that was a nice property then. And when telephone companies started to digitize telephone networks, they thought, well, okay, our old networks had this nice property. Of course, we want new networks to have the same property. So they developed protocols and network technologies to try to meet this requirement. And of course that is much harder in a digital network because you don't have a physical link between the two people. You are sending a signal into a network and then it bounces through different routers and eventually arrives as a packet somewhere. And you have a stream of packets sent, and that stream of packet is merged with other streams of packets. So it's much more complicated. But that was the idea, and they developed then these, for instance, the ATM networks, asynchronous transfer mode networks, that try to have this property, which means that when you started a phone call, the first thing you had to do was to establish a connection to the other side. When you did that, you allocated resources along the way. So all the different nodes that were involved reserved capacity for your phone call. So it had buffers, it had capacity on the line, so it can guarantee that your phone call could be sent without interference. But that limits the flexibility of a network, and it's quite costly to allocate resources in that way. Because say an typical phone call conversation, you talk for a while and then maybe you're silent for a second or two, and during that time you don't really need to send any data, but still you have allocated resources in the network to handle it. So you're wasting resources. But that was the idea. Today, more or less, they have left that idea and instead try to compensate for the jitter that we have. And we'll talk about that later on, how we can implement that. So we have throughput, we have delay and jitter as three different components that we would like to measure and possibly think about when we are establishing a network connection. Let's see how they are dependent to each other. Well, obviously jitter and delay are very closely connected to each other because jitter is just an extra property of a delay. But throughput and delay are also actually connected, even if they are, in theory, they are totally different things. I mean, how many data packets we can send into a network and how long time it takes to reach the other end doesn't necessarily relate to each other. But they do affect each other. Because, as I said, delay has this variable part, the queuing part. And the more data we send, the more probable that queues will start building up. Which means that when the more data we send in, the higher the throughput we're trying to get, the more problem we will see in the network with delay. And of course, ultimately there could be a congestion or a deadlock even. So the network is so full that we couldn't accept packet anymore and it's entirely deadlocked. It couldn't continue at all. We have to restart it. That rarely happens today. But congestion happens, of course. So to talk about this relation between throughput and delay, we introduce a new concept called utilization. The utilization of the network, how much of a capacity are we actually using? And then we can put up this relation here between the delay in a network that is not used at all and delay and the actual delay that we see. So you see this formula here. D is then the effective delay that we see currently. And then that is dependent on D0, which is the delay in an idle network. If we just send one packet and the rest of the network is not used, of course that packet will rush through the network without any queues. So that is the shortest delay that we can get. And then we divide that time with this difference between 1 and the utilization, the current utilization of the network. So the utilization goes between 0 and 1 then. 0 means it's not used at all network, and 1 means that we are using it as full speed. We are pushing the network as much as possible. We are sending packets all the time without any interruption at all. So obviously below here we get a number between 1 and 0. It reaches 0. And when it goes against 0 here, well, what we'll see then is actually a curve of utilization that looks like this figure here. So this is the effect that we'll see here. Let's see if we can. Switch to camera.
There is a question in the...
Yeah, okay. What is the question?
What is the term for when we want to send a packet of data faster than a second instead of sending more data in 1 second? I don't really get the question.
The term for when we want to send a packet of data faster than a second instead of sending more data in 1 second. Yeah, no, I don't get it. I've actually tried to rephrase the question, please. We'll see if we can understand it. Thank you. So if we see this figure here, we see that the utilization goes between 0 and 100%, or 0 and 1 then, if we have this measure 1 to 0. And if we start to use more of the network, utilization starts growing. Initially, nothing much happens actually, because the network is capable of handling the load very well in the beginning. Almost all packets get through directly. Queues don't start to build up until the utilization starts to really grow here. And when this happens is really dependent on the type of network that we have. A token ring network compared to an Ethernet network have different behavior here. So a token ring network, for instance, is much better at handling high loads than an Ethernet is. But at some stage we will see the same thing. So it's just really how the shape of its curve, it can be a little bit different. But more or less the same. Not much happens in the beginning here. Latency is quite low, but suddenly it starts taking off. And when we are getting close to 100% utilization, we almost have infinite delay then. And this is something that we couldn't do much about. There are network protocols that tries to handle it better, but a network can never work efficiently when we are close to 100% utilization. So for that reason, typically when you design networks, you always first analyze what type of traffic will I have in my network? What are the loads? Yeah.
How about if you use a mesh network?
A mesh network will have the same result. It will be more resilient. So it will take a little bit longer time before it starts to see, but it will see the same trend after a while. It's just that in a mesh network you can take different paths, but eventually all the paths will be utilized fully, and then we'll see exactly the same thing again. So it won't help. So typically what you do when you design network, you start to look at the loads that you foresee, and then you design your network to take care of that. And well, as you see here in the numbers, you may have an idea that we should never have more than 50% utilization. Some network designers say not more than 25% utilization typically. Then of course there will be peaks sometimes, but normal traffic it shouldn't go up. So as soon as you start doing that, what do you do? Well, you add capacity. And we said that capacity is easy to add. You just buy more lines or upgrade the lines you have. So capacity is something that is easy to get. So you always have to monitor to see what is the current utilization of your network. Let's take a break here and start 1/4 again. Did you get the new question? No?
I have a question.
Yes.
How does the graph look of throughput versus utilization? Because if we have low utilization, if we're not utilizing, for example, if the link is 10 megabits per second,
Yeah.
and we say we enforce that 25% utilization limit, then we can only send 2.5 megabits per second, right?
Mm.
So we kind of want to balance latency and throughput, right?
I mean, utilization is really how many percent of the capacity we're using. So I mean, it's a straight line. You increase, the more you send, the higher you're utilizing the network until you reach maximum, and then you couldn't reach more than that. But
Yeah.
But typically, as I said before, you can never reach 100% because there's always overhead that will stop you from reaching the full capacity. So you couldn't really reach 100%, but you may reach 90-95% perhaps.
How about the direction if you upload or download?
Yeah, that can be different. I mean, most networks are built in a way that you have the same in both ways, but it's not always the case. And sometimes you send traffic in one path and the return traffic takes another path, and then it can be very different if you go through internet. So yeah, that's why you have to, when you measure round trip delay, for instance, you really need to think about, is it the same delay in both directions, or maybe one direction contributes to most of the delay? And then if that is the case, you have to sort out the problem in another way. Okay, let's see here. Just for the streaming, we'll add 10 minutes break. Yeah.
So working hard.
Yes.
on
Have you done the? Yeah, I'm trying to construct it in mind map as a mind map. Takes hours me to take
I
more.
use draw.io.
Yeah, but it depends on the network. Mine doesn't depend on the network, and I have the same version, so synchronized.
Oh, really?
Mm-hmm.
What kind of app is that?
It's eDraw Mind Master. And
Oh, I think I've heard about it, but
yeah, and
it's
I have
probably paid,
the
right?
same- No, it's free,
Okay.
and I can open the same
Nice.
map in sheet one.
Is that for your other class? Is that for your other class, or are you just playing around with software? Like, what are you using it for?
I use it for everything. I use it to schedule my days, to
I just use the notes
to
app. Pen and paper.
yeah. Have you done the Digitask for 70?
Yes.
Both of them?
Yeah, everything.
I
too, right?
Hmm?
You too, right?
No, I couldn't do post method.
Post.
Put method. Yeah, I
Was
did post method.
when you uploaded data, regardless of put or post, was it encoded to base 64?
No.
Thank God.
It may be, but normally no. I just I used actually I used Kuro application. Do you know?
Say it again. Kuda?
I used
Kuro?
Kuro. This one.
Whoa. Oh, girl, yeah.
Yeah, and I tried to post post method with this one instead of form, instead of HTML form, and it works. It sends data,
Mm-hmm.
then it's supposed to receive an answer to continue, and then it sends an actual file.
Mm-hmm.
So it's
Weird. Ours worked without sending
and
continue.
yeah, and the HTML works another way. It just sends
It just
everything.
dumps it.
Yes,
everything.
yes. That's why I'm not sure if I accomplished.
Yeah. If it does, is it when you send it with curl? Is it like instant?
No, you send it and you wait until you get 100 requests. Yes, can you need continue, and then it sends data.
The request you get will have a header for expect,
Mm.
like continue.
Continue.
If
It
it's
expects continue.
waiting for a continue, but
Mm.
the HTML form way, it doesn't say that.
Yeah,
but
yeah.
that was like a
That's the
switch
point.
to
That's
it.
why my application works only with curl and
Ah,
doesn't
okay.
work for HTML. I
Ah.
tried to fix it, but I didn't have time.
Okay, I see.
Yeah, when I realized that those two applications send
Oh,
data in a
you probably
different
said
way,
the
and
expect You probably sent the 100 expect to the browser as well, right?
Do you have the code up
don't
right
think
now,
so.
Ruslan?
Hmm?
Do you have the code up right now?
Yes,
Can I look at it?
yeah.
Because I was having so much trouble actually like decoding what I got from the HTML form.
He didn't get base 64 either, so.
You didn't get base 64.
Yep.
Give me
It
a
must have
second
been
to
like.
turn on
Can
the
I look at
server.
your HTML form? I just want to see like.
I don't have it on this computer.
Mm. Okay. So basically, if I do like this with V, it will show all the headers I sent. So it sends and it
Expects.
expects
Yeah,
100 to continue.
Yeah.
Then I send 100
Mm.
expect,
Yeah.
100 request, and it actually sends the data, and now my server can handle the data and do some stuff to divide headers from the actual part, because it also it sends not only the bytes but also another header.
Yeah, it sends like does it send it in the
This
form
one.
of like
Content length.
content type. Okay, so
And,
it does
and
send
this one as well.
multi-part form data. Okay,
Yeah.
so it sends the boundary and then you parse
Mhm.
that out of
And
the
and
thing.
also I believe it's
And the fuel
has
is-
some or something.
Yeah, it's unique, I think. But like, so it's basically I had like a problem with it, but like I had this plus extra crap, so I was trying to sort out what was extra crap and what was bytes that were related to the picture, and it was a pain in the dick and balls.
Did you parse the multi-part with a scanner
No,
or like some other?
no. I didn't even get started on decoding it. Like by this time I'd spent like 6 or 7 hours just trying to get the data
Hmm.
from my stupid HTML form.
And I know I take all the data, then I count. I put it into let's say I decode it into a string,
Mhm.
and then I count how many bytes of the entire data is actual string and how many bytes is data. And then I just subtract all the initial data, all dot bytes from both ends.
Did you? So you basically hard counted like the amount of lines it took before the data started, or did you count like did you check for the header,
I check for
or
the header.
you
Yes.
scanned for the?
No, actually I divided break line means the header is finished.
Yep.
So I divide it into two parts, and then I
Discard.
try to discard. I say okay, this is text and this is data.
The cat
The
is out of the box.
how did you receive your packets? Did you read it into a buffer or how did you?
Yes, in the buffer.
Okay. What did you do it? Did you do it in like a loop in case your buffer got full or?
No,
No?
Actually, when it's about to send data, it says
Yeah.
how big the data is about to send.
Mm-hmm.
Then, so I prepare the buffer of exactly the
Oh,
same.
so you get a new buffer for
Yes.
post. Okay, okay.
Yes.
And is that in
I don't
bytes
think
or?
that's it sends for the multi-part though. When you send an image, it doesn't send the content link. It only sends the content link of the
How big
entire
of-
body.
How big
No,
of
no,
switches
it's,
do you
it's
try to
actually
play?
it sends me the amount of
Yeah.
of the entire package it's going to send.
The
So I
body
can
of the
prepare
device.
buffer. I say, okay, I have buffer. I will have buffer exactly the same, and all the message is fitting within the buffer.
Cool.
it's normally
Yeah, I did mine in a loop, so if as long as I still had data, the buffer would I would keep filling the buffer, putting
Yeah,
it in
yeah,
a,
yeah.
in like,
But it's tricky. No,
it's tricky, but so I
it's much
kept
easier to
I kept
to know
cutting off
how
my
much.
connection. It would be like it would be reading, right? And it would think there was no more available because like the form hadn't like fully uploaded everything yet. So like the data stream coming in would be empty because it hadn't been filled on the other end.
Yes.
And so my server would be like, oh great, I'm done, and then just cut off like half the thing. So I was trying to figure out some way to make it wait, but I couldn't. I didn't think of using the constantly.
They say half
So
a
they-
month.
Yeah, it's hard part.
But I got put. So
But for post,
That's
it's basically the same. Post and put,
if
they
you're
are
fast enough. And
more or less the same. The difference is you can
It's like
do whatever you
early
want with
the
post, and
60s
you just need to
in
keep the
Africa,
file when
Ebola.
when it.
it doesn't have time to travel
Basically,
so
just
far
put like,
because it's
so it should be more like
fast.
Thank you.
Yeah, no.
It's been
create if doesn't exist, replace if it exists.
Yeah. Or change another name, or send back
And that's
some kind of
a very
success report or something.
compared
Because you can, for example, from the data
and the
you
coronavirus, we don't know how
in post,
that it
when
is.
you send the file,
Some
and the server handles it, and it can say, no, I won't save it because I already have this version somewhere, or I will resend it, and it can answer what you have done in the file back.
So you think I'm wearing? He thinks I'm wearing a hoodie.
There's not a lot of people left
From
in
the
this
north.
class.
Probably a lot of people watching online.
No,
But it's
And,
See how many people are watching.
because
On the
if you look at
see it right now, too.
it,
Let's see how many people are tuned in.
You need to-
1% or less. So we're reading too much of it.
it's open. And now it's going to open, so at once. Of course.
Not many people watching.
How many?
You remember the first day of the operating system? That's when it was full. Like, I think it even overflowed. There was not enough space for everyone. And now it's like down to 10 people.
I'm not sure if this lecture is going to be recorded or
Yeah, they post it later.
Okay, so the stream working? Yes, seems to be working. Yeah. Dropbox is full. Okay. Got another question, Slack. So, are new technologies such as new protocols, hardware, and standards only upgrading hardware to enhance the throughput, but not the utilization rate? Yes, I would say that. Especially if you talk about hardware. I mean, hardware is really getting more capacity. We are getting more throughput. It's software that tries to deal with utilization, trying to use the hardware as efficiently as possible. And if you look at protocols, and especially the type of protocols we talk about here, that is really the backbone for internet, that is changing very slowly. So not much is happening with utilization. So the focus is increased capacity, but utilization is more or less at the same percentage as before. Of course, we get more utilization with more throughput, but not higher percentages. Right, so that's what happens if we look at delay and throughput together. So the more utilization, the more throughput we actually are putting into the network, the high delay. So of course, if delay is an issue, we could handle it by reducing the transmission rate. That would help. But if that is not a working solution, then we have to add more capacity then. We can also look at this, the delay throughput product. We multiply the delay with throughput, and that will tell us how many bits are in the network right now. So we put in 100 bits per second, and the delay is 1 second. Then of course we will have 100 bits in the network. If the delay is 10 seconds and we put in 100 bits per second, then suddenly we'll have 1000 bits in the network at one time, at each time in space, or sorry, not in space, but at each time point. So it gives us an idea about how much information is really in the network. And what can we do that? Well, it can be interesting to see how much information we have there if the network goes down, for instance, suddenly. All that information that is in the network now is lost. How do we deal with that? Is this something that we need to deal with by making sure that we have copies so we can resend it, or is it information that can be lost? So it's not a super important thing to know, but it's good to have an idea at least about how much information we actually have in the network. So how can we measure these things then? Well, starting with throughput then. We can measure throughput in this way. A sender transfer a large volume of data, a big file, and we push the file packet by packet. A receiver then records the time from start of data arrival until all data has arrived. So now we know how much data it is, and of course we know how long time it took to get it through. So now we can measure what the actual throughput were from sender to destination. So that's one way. If we want to measure it the other way around, we do the same thing, send a large file or a large amount of data the other way around. So this is what Bredbandskollen, for instance, do, or TP test is doing here. But we send a large sum of data, and then we measure how long time does it take for that data to arrive. Of course, we have to think about packet loss that could happen. How should we handle that then? I mean, packet loss can happen, and if we are only interested in throughput, we shouldn't probably resend, so we should just notify how many packets were lost then, but calculate the throughput depend on the rest of the packets. Packet loss can itself be interesting to measure, because if we have a high packet loss, that indicates also we have a problem in the network. That could be that we have congestion somewhere in the network, or it can be a faulty network configuration or something else. So high data loss is something that we really need to look at. Jitter is measured by a packet train, as you see. So the sender emits a series of packets with a fixed delay, and that fixed delay can be, so we're just pushing packets, or it can be a fixed delay, so we actually wait for 50 milliseconds or 100 milliseconds, something like that. Now it's not important to send a special amount of packets. We just continue to sending packets for a while, and the receiver just measures then the time interval between each packet when they arrive. and then we can calculate the jitter, the variation over time. So we have to continue doing this for a while, of course. Can be for a minute or for several minutes to get a good indication of what is the actual jitter in the network. So these are easy because we only have to send from one and then we measure on the other side. The delay is harder to measure because delay means that either we have to have synchronized clocks between sender and destination, because if we send a packet, we can put a timestamp on it. We know when to send it, and when it arrives, we can look at that timestamp and compare with our clock, and then we can see how long time it takes. But in order for that to be accurate, the clocks have to be extremely well synchronized. And it's hard to synchronize clocks so good that it's enough to get a good measurement here. So the alternative is instead to do the round trip time. We send a packet and then the other side just returns it immediately. And then we measure the time on both ends, and then we say that, well, the delay is round trip delay, and then probably the delay in one direction is half of that. But we couldn't really know that because the paths doesn't have to be the same in both directions. So it can be very different delay in one direction and the other direction. Ping is doing just that. Ping is calculating round trip delay. So if we send an ICMP echo request, which is what ping is doing, the program ping, the packet is sent, and at the other side it's just returned with an echo reply. And then we measure the time between when we sent it and when it arrived back.
Can't we allocate resources through the line and measure the delay that way?
Allocate resources, you mean decide on which path we're taking, or how do you mean?
Yes.
Well, on internet you couldn't really do that, right? I mean, you don't have any control of a network of internet. And that is part of the beauty of the internet. You put an IP address on a packet and then you push it onto the network, and then you don't have to think about it. It's up to the network to deliver it to the correct destination. But if you talk about the ATM network arrangement before, that was exactly what you're saying. You have to allocate a route before, you have to allocate resources, capacity buffer and so on, and then you know that you have a path, and then you could also have more or less a fixed delay. But that's not how internet works. So.
But you can measure part of the way if you know which part.
Well, if you can synchronize clocks, you could measure any part of it. But synchronizing clocks good enough is hard. I mean, even if we need to have these atom clocks then that we have, for instance, in GPS system today. That is accurate enough, but you don't have that in a normal computer, unfortunately. We should also think about how we measure things and how that actually affects the network. Because whenever we do any type of measurement in networks, we can either do it actively or passive. And passive means that we don't interfere with the network at all. We just listen and capture information about the current state of a network. So we put in different monitors, and we can do that either in normal hosts, or we can put them in different type of active equipment like switches and routers and so on. They can have these monitors that measure what is going on in the network. Active instead is measuring by actually sending traffic into the network and see what happens. So that's what we do if we calculate jitter or calculate the throughput. We have to actually inject traffic. And of course, while we do that, we affect the performance of a network for other users. So active is something that we couldn't do all the time because it will take too much resources for a network. That is something we can only do now and then. But passive we can do all the time. Of course, in order to use that information from a passive measurement, we need to gather it somewhere. And how do we do that? Well, normally all our network equipment is connected in a way that in order to do something with it, we have to use the network itself to manage them. Which means that in order to collect that information, we actually have to send it through the network. So we will affect the performance of a network. But that is very small compared to the active type of measurements. So passive can be done then by different equipment. They can look at packet loss. They can look at how much packets that are sent on different interfaces on different networks. They can measure delay, at least through their own device, to see how much they add to the delay. So there are different things we can do passively. And one standard is this net flow standard that is just doing that. If we have active equipment, not only from Cisco today, it's supported by other manufacturers as well, you can put the device into a monitor mode to actively collect this information and then pass it on using this net flow protocol to a management station that can then get information from many places of the network and get a good idea of what is going on in the network. Are there parts of the network that is congested or even we couldn't reach part of a network. A port is closed or something like that. So that's what is reported with this net flow standard. Now let's move on to quality of service. Performance and measurement of performance is just to see what is it. Quality of service tries to turn it around and say, what would you like to have? What properties do we want from a network in terms of delay, variance in delay, throughput, and so on? So that's the purpose of quality of service, to try to get, you can say, a contract between the user and the network, where the network says, okay, I will deliver this to you. These contracts can be very simple or they can be very complex. The easiest type of contract is the type of contract that you probably have with your ISP in your home. You have a contract saying that you have a 100 megabit connection to internet, perhaps. And what the contract says is that is the maximum you have. So it's not a very good contract for you because it only says the maximum you have available. And there might be some wordings in that contract to say that normally the ISP should make sure that you at least in 95% of the time have at least 80% of that or something like that, but very vague normally. And for our purpose of that is probably enough. But other application areas, when it's not enough, we need to have better guarantees on that. If we then look at how to handle the quality of service in a network, we have these two main approaches for it, a fine-grained and a coarse-grained approach. And the fine-grained approach, the idea is that each data stream that we start over network have some requirements. We have an application that have a connection with some other application somewhere on the network. They need to have some properties of a network in terms of delay and how much information we can send per second and so on. On the same machine, there could be another application that has another connection, and they have other demands. They may want to have the possibility to send large amount of data now and then, but there's no requirement of delay for that application. So each application creating a stream could have different requirements. And with a fine-grained approach, we give the network try to meet each stream's requirement then. And the easiest way to think about it in TCP/IP networks is for a TCP connection. We establish a TCP connection, and then at the same time we have some requirements on that TCP connection. A coarse-grained means that we don't look at each separate stream. Instead, we just say that, well, there are different types of traffic in the network. So let's try to classify them somehow. And then different classes of traffic is handled in different ways. We might prioritize some traffic over other. But we don't look at specific connection, we only look at traffic types. So these are two different levels of quality of service then. And we can probably directly see that a coarse-grained approach is much easier to implement, while a fine-grained is much, much harder to implement. But let's start looking at fine-grained then. So that is that each application has to know its requirements. And then we have to make a contract between the user and the network. And then when we write that contract, the network can say, well, I can't give you that. Or it can say, yes, I can give you that. And this typically can be on the fly then. Each time when we create a new connection, we have to go to the network and say, okay, I have a new connection here. I would like to have these requirements on this connection when I connect to that other computer over there. And then the network has on the fly to come up and say, okay, I can give you that, or say, sorry, I can't give you that. This is the idea from the telephone system, where we want to give each telephone call, that would be each connection here, a certain requirement in terms of data speed and delay. If we look at the types of requirements that we can ask for, that is something that has lived on through these old types of networks. So the terminology is still used, where we talk about different levels or different types of services that we can ask for a network. So see, constant bit rate means that data enters the flow at a fixed rate, typical phone call, for instance. So we would like to be able to constant have that bit rate. We won't have to go up, but we have to keep that bit rate. Variable bit rate means that we can have a variation then instead. That would be harder for the network to accommodate. So to accommodate that, we would have to give some bounds for it. We can say that typically it's maybe 10 megabit, but it can go up to 50 maximum. And but the mean is 10 perhaps. We have to give those type of statistical data, otherwise the network couldn't try to live up to it. But that's hard, of course, because then the network have to be able to handle the maximum load now and then, instead of just a constant. Available bit rate is much easier then. The flow agrees to use whatever data rate is available at a given time. So we're not guaranteed any real speed or throughput. Why would we agree on that? Well, probably because that quality is much cheaper. So for some application, we can live with that. And if it's cheaper, then fine, we do that. So in a network, we probably would like to have either only constant bit rate or a combination of these variable and available, because then we can more easily accommodate the variable, because we just throttle the ones that have this lower type of quality of service. And then we can have this unspecified, which just means that the network gives us best effort, which really internet today is doing. So depending on which of these quality of service, we have to give different types of input before the network can say, yes, I can agree to this or not. And the variable is tricky because we have to give upper bounds and statistics. Constant is easy because it's just a constant and so on. But that's just the bit rate, but we also have to talk about delay, for instance, as a parameter that we can agree on. So that was the idea with fine-grained. It was built in the early telephone systems, when telephone systems were digitized. And when internet was starting to grow, they also looked at this to see, can we give that type of quality of service on internet? So there was a research on what we call integrated services, so INTSERV, with a focus of trying to give fine-grained quality of service on internet. But unfortunately that didn't really work out, because it was impossible to really give this quality of service at this level. We'll come back to the problems here. So instead, they went the other direction and look at coarse-grained quality of service. Can we implement that instead? So, as I said, in coarse-grained we classify traffic instead in a number of classes. Typically not very many. 7 classes perhaps, something like that. So all the packets have to belong to one of these classes. And then whenever a router gets a packet on a network interface, it just classifies it to decide which of these classes does it belong to. And then depending on that, we decide on how to handle it. And what can we do? Well, we can either pass it on directly, or we can put it in a queue and hold it for a while, delay it, and prioritize something else instead. So that's really what we can do. We can prioritize different type of flows more than other types of flows. This is much easier then compared to fine-grained, because think about what fine-grained would require from a router. Think about this core router that have internet that handles millions of flows at the same time. For each of that flow, we need to know exactly what are the parameters for this flow and try to meet them. For coarse-grained instead, we just have to classify each packet in one of 7 classes and then decide what to do it depending on that. Much, much simpler than having details of each flow and trying to live up with the requirements of each flow. So coarse-grained seems to be a much more possible way to actually implement quality of service. So there have been different approaches actually to implement coarse-grained quality of service on internet. There have been several different standardization over time with different protocols. What they try to do is they try to typically use something that we already have in IP, because it's IP packets that we try to prioritize. And if you think about a header in an IP packet, do we have any field that we can use for classification in an IP version 4 packet, for instance? Do you remember any field that we could potentially use to classify it?
Differentiated services. Or what?
No, well, differentiated services is an added protocol that we would use. But if you think about an IP version 4 packet, there are some fields. We have address, right? We have this time to live. We have checksum. There are some fields here. But there is one field that is not really used very much, and that is what's called type of service, or TOS field, which is just a few bits. The idea with that initially was to declare what is the type of service that we have in this datagram, what is the type of payload. But it wasn't really decided when IP was invented what it should be used for. So it really just sits around that, waiting for someone to use it. And use it for quality of service is something that we might use it. So the idea is then in this type of service we put in different categories then to classify our traffic. Let's see if I can find, I didn't include that, but let's see if I can bring it up. Yeah, here we have. These are typically what we can put in here. This is always called the PCP. This is one of the standards that try to use this in order to classify traffic from 0 to 7, as you see. With 0 being default, best effort what we normally have on the internet. But then we can say that 4 or 5 are for different type of video or voice, so streams. We have something called network control. That was typically the idea that if we have an SSH connection to another machine, but we want to control, send commands on it, that should be high prioritized, so we can control things. And then there are a few others. But you see, any application that sends something should choose one of those when we create the datagram. And then routers should then look at each incoming datagram, look at this field, and then based on that decide on how to prioritize packets. And typically, I mean, control packets should be high prioritized. So we can always control things. Even if the network is crowded, we can still manage the equipment. Streams should be prioritized. A little less, but still quite high, so we have a good flow in different data streams. While best effort, for instance, is very lowly prioritized. The obvious problem here is that there are no guarantees at all. What we say is that we classify the traffic, and then it's up to the network to try to do better than just best effort with some of it, but there are no guarantees at all. So the quality is not much better than no quality, actually. For IP version 6, we have similar fields in the header as this type of service that we have in IP4. So the idea has continued with IP version 6. And there are actually several different protocols that try to use this in order to control how we prioritize different traffic. But regardless of if we use fine grain or coarse grain, there are several steps that the router need to do in order to implement quality of service. So typically we have these 4 phases. So think about this as a router now. We have an input interface here. A packet arrives on one of the input interfaces. We already talked about last time, what do the router do? Well, typically the router is doing forwarding, right? We look at the destination address, we look in our routing table and decide, okay, that packet should be forwarded to a certain output interface, and then we just send it on to the next router. And that's what we do here in the forwarding computation. But if we look a little bit more closely on it, we actually do more than that in the router. So actually we have 4 phases here: classification policing, forwarded, output queuing, and traffic scheduling. So let's look at each of those steps then. Classification and policing means that when the packet arrives, we start looking at it. If it's fine-grained call as a service, then it will have a flow tag or identifier, so we know exactly which flow or which connection this packet belongs to. And then we look in our table and say, okay, this packet belongs to this flow. We have made this type of guarantees for this flow. So now we know where it belongs to and what we have agreed on. If it's coarse grain, we just look at this type to see, is it something that with only best effort, or should we try to do better than that? But that's still what we do here in this step then. Once we know what a packet is, we do policing. And policing means that we check that the packet lives up to the agreement we made with the sender. Say we have an agreement with the sender to say we want to have a steady stream of 10 megabits per second, constant bit rate. And suddenly the sender starts sending at 20 megabits per second. That means that the sender is violating our agreement. And we don't have to live up with that. So now what we can do is we can start deleting packets. We only need to forward what we have agreed to forward. If we try to forward more than that, it will probably affect some other customer, so we shouldn't do that. So policing means that we are actually deleting some of the traffic which doesn't meet our agreements. For coarse grain, we probably wouldn't delete traffic. We only know at this stage what it is, what class it belongs to. Then we have the next step, forwarding. So that's what we typically do. We look in routing table, and we typically have several possible, let's say we are in this router here, 3 different interfaces. A packet arrives on this interface. We have to know which one we should forward it to. So that's the normal forwarding computation. Nothing strange with that. The next step is output queuing. And this is an important part of quality of service, because in order to give some quality of service, we need to have prioritization of traffic, as I said before. And one way to do that is actually to have several different queues for each physical interface. So here we see in the figure here that to the right we have just one physical interface. So we can only send one packet at a time. But we have several different queues that we can put traffic in. And as you see, we call them class 0 to class 7, and we have different queues for unicast and multicast traffic. And where we put them is dependent on the information that we gathered in the first step here about the classification and policing. So now, after that, we know which queue we should put that packet in. And we know which input or which interface it is depending on the forwarding table. We can have many different queues, or we can just have a few queues. It depends on how fine-grained our quality of service is. But there typically is more than one queue at least. So now we are in a queue, and of course the idea is that some queues are slower than other queues. So we already know that if we end up in a slow queue, we'll have a worse service than if we are in a faster queue. But now we come to the last step here, and that is the traffic scheduling. Now a lot of packets are in different queues. The traffic scheduler now decides which packet should go next on the output interface. And that is the main part of the quality of service, because here we decide from which queue we should take the next packet. And the traffic scheduler could say that as long as we have anything in the highest priority queue, we always take from that queue, and everyone else just have to wait. Or we can say that half the packets that we send out, at least half a number of packets will be from the priority queue, and then 25% will be for the next queue, and then the rest of the queues will have to share the rest 25% of the capacity, or whatever. There are lots of different ways to do the scheduling, but the scheduling is where we try to actually meet the quality of service agreement. Can be very complex, or it can be simple. There are some, here we see some example of schedulers, how they can work. Leaky bucket allows a queue to send packets at a fixed rate by incremental packet counter periodically and using the counter to control transmission. So a leaky bucket would give a constant rate from one queue, and then it can take a variable rate from other queues perhaps. Token bucket allows the queue to send data at a fixed rate by incremental byte counter and user counter, so similar to the leaky bucket. We can have this weighted round robin, just goes round through the queues continuous, queue 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so on. But it could be weighted, so it takes 1, 2, 3, 3, 4, 4, 4, 4, 5, 5, 5, 5, 1, 2, 3, 3, 4, so it doesn't take the same amount. Or this deficit round robin, who has a variation where we can, the weight is more dynamic. These are just a few. There are lots of different ideas on how to make this scheduling algorithms actually. If you set up a Unix workstation as a router, you have that already in the Unix distribution, the possibility to do that. And then you also actually have support of a lot of these different traffic scheduling. And you can use that in order in your home. If you set up a Linux router on your output interface, you could control and do some of the quality of service, so you can prioritize, for instance, streaming, video streaming, and put lower priorities on web traffic, and then you can get better performance perhaps on the video streaming. This is also something that is more or less implemented in many home routers today if you buy normal routers. So they use some type of scheduling often. So examples of protocols then that we actually have on the internet then. Well, there are a number of protocols. We'll mention a few here: RSVP and COPS, diffserv, and MPLS. So let's start with RSVP, the Resource Reservation Protocol. So that is a fine-grained approach then. We try to actually allocate resources in the network. So it works by all the routers that are taking part of this are communicating with each other. As soon as a host wants to set up a stream, it has to use this RSVP to communicate with routers. We send a probe packet through the network using this RSVP. All routers on the way are checking if they can live up with this demand or not. If they can, they allocate resources and pass it on, and eventually it goes to the other side of the network, and then we get the packet back and say, okay, everyone can agree, we can create a flow that can live up to this. So this is the fine-grained approach then. If we agree we have a flow identifier, so we identify each flow separately, and then each router would then try to honor that as best as possible. COPS, the Common Open Policy Service, is a companion protocol to this RSVP. As I said, to specify and enforce policies. The idea is that in a network we have a number of routers, and RSVP is used in order all the time when we set up flows to negotiate that. But COPS is used when we would like to decide on new policies for the network as a whole. We would like to say that, well, in this network now, from now on, we would like to prioritize this type of traffic over other types of priorities. So with COPS, we can tell all the routers, you should work a little bit differently now from now on. So it's a way to control the routers that are using RSVP. So this is fine-grained. Obviously, this would only work if all the routers were implementing RSVP, because as soon as a flow enters a router that doesn't know about RSVP, we couldn't give any guarantees anymore. And RSVP is not used throughout the internet. So it would only be working if we have a local network or an autonomous system when we have control of everything. So we can use it within that. But on internet as a whole, it doesn't exist today. Then we have the diff serve. With this type of service, as I said before, we try to allocate them, and then the routers, as best they can, prioritize different type of traffic over, but we don't have this fine grain, it's this coarse grain idea. There have been some experimentation with this, and there are several different actual protocols to implement this in different ways. And it is used in places, but there are no guarantees that it is used throughout the internet, which means that if we send a packet of some sort and we mark it, there are no guarantees that all the routers on the way will actually look at it and bother about this information at all. So we can mark, and hopefully it will help, but there are no guarantees, again, on internet for this. So if you look throughout the internet, there are really no quality of service that we can get today. What we can get is quality of service in limited part of the network where one network provider has control over all the equipment. And the modern way of doing that is with another protocol, this multi-protocol label switching, MPLS, which is quite different actually from what we already looked at. IP, as we know, is a layer 3 protocol. It's on the network layer. MPLS is considered to be a 2.5 protocol, so it's below IP level. So it's between the network and the physical links, the data links. For MPLS to work, again, all the routers need to be MPLS aware. So again, it would only work in a limited network. But in a limited network, this is a very efficient way to get quality of service, actually. And that is that at the end of a path, and the end of a path is a border router between the normal internet and our MPLS network. So what happens is that the border is that datagrams are encapsulated into an MPLS packet. And then throughout the network, we don't see it as an IP datagram anymore. We see it as an MPLS packet. And we forward MPLS packets. And before we can do that, we have to set up an MPLS path through the system. So it's very similar to the idea of a fine-grained approach. We have to set up these paths through the network. But Now we talk about the limited network, of course. And when it reaches the other end, we extract the datagram from the MPLS packet and forward it on the other side. So the effect, this is again something you may have at home. Your ISP is probably using MPLS, even if you don't see it, because what you see is on the other side here, they pack up and deliver a datagram to you. But in their internal network, they probably, there are options, but they could use MPLS to control the traffic within their own network. And one reason of doing that is if you have, for instance, if you want to separate video streams from data streams and from voice streams, you allocate certain channels to them and handle them with the MPLS to get quality of service. So it would look like something like this. Here we have internet, some service on the network. They have no idea about your MPLS network. They doesn't care. They only know the IP address of the destination. So that is what they put. They create norm datagram. It arrives here at what we call an ingress server. That is the entry point to our MPLS network. What happens here is that we encapsulate it. See, the blue IP packet now gets a beige MPLS header. And in that header we now have an MPLS label. And then we have to set up a path for our network. So we have to allocate, we send a probe packet through the network to allocate resources in all the routers. And then we just do switching really when we send it, the packet after that. So it enters an router, we just make a quick lookup, and then we just forward on the interface based on just that label that we have in the MPLS header. So the switching is very fast. So the delivery of packets in an MPLS network is much faster than routing in an IP packet. So that's the reason, one of the reasons to use MPLS. But another reason is that we can have different flows and we can have prioritized between them, so we can get the quality of service as well. So eventually it goes through all of them and then it reaches an egress router here. We remove the MPLS header and we pass on the datagram. So what we see on that side is that the datagram, we have no idea that it has gone through an MPLS network between sender and destination. So these are different protocols to actually implement quality of service, and MPLS is the modern way to do it, you could say. You had a question?
Yes.
Yeah.
What is a packet comes already with MPLS header?
Well, it couldn't, because on the ingress router here, we only accept IP datagram here. It couldn't come an MPLS packet here because in order for it to come, we first have to allocate a flow label to it and we have to agree on that. And unless we have agreed with our router over here, that couldn't happen. So the only way to do that would be that we move the ingress router over, and then that would actually be part of the MPLS network then. So on the internet, we never have MPLS packet, we have datagrams. But in different parts then, when they pass through one ISP or network operator, it may be forwarded with MPLS, but we never see that.
But it can come by mistake or something?
No, it could never happen, actually. Are there any questions on Slack? No, I don't think so. Okay, so we stop for today, and on Thursday there will be a lecture in Kalmar that is streamed. I will publish the last assignment probably tomorrow or Wednesday, so you can start looking at it. So keep your eyes on Moodle. Okay, thank you for today.